All right, in this one, we're going to take a look at adding multiple vectors with multiple different angles. So, for example, here's a problem that we might have to solve using our newly acquired vector math. So, what we're going to do in this video, what I'm going to show you, is as we talked about in the last video, when you have a vector, like if you look here, we've got a 5 meter displacement vector. So a woman walks 5 meters east. She then turns and walks 30 degrees north of east for 6 meters. And then she proceeds to walk at 40 degrees south of east for another 7 meters. So we want to find her displacement, the resultant displacement from the beginning here to the end here. So we're trying to find this line. But the vectors are at angles. Okay, so the way we're going to approach this problem is we're going to break all the vectors that are at angles, so the red and blue vector, we're going to break them up into the x and y components, and then we can add those together to make just a final 2 vectors that we can then add together to make our resultant. So what I'm going to do for this technique, so when you have multiple vectors like this, is to make a table like this. The table can look something like this. And we're going to start with our black vector. So I'm going to label this vector here as vector 1. So vector 1, and I have the directions here, north, south, east, and west. So vector 1 is 5 meters, and it's in the east direction. So it has 0 magnitude in the north, 0 in the south, and 0 in the west. And it's got 5 in the east. These could also be plus y and minus y, plus x and minus x, or if you wanted to do something like that, or if the problem calls for that, that's okay as well, okay? But I'm going to use north, south, east, and west. We have our directions right here in the corner, you can see. So then let's take the red vector, vector 2, and let's break it down. All right, so to find the resultants of this vector, we could either draw this green-purple line here, right? Because if we do this, we will have the y and x components that make this vector up. That's okay. We could also draw the x and y components here. So either way will work. If I do this x and this y, right? I'm going to use this x and this y. I'm going to use the angle of 30 degrees. If I do this y and this x, I'm going to use the angle of 40 degrees. Okay, so either way will give us the same answer. So since I originally drew this in this vector, I'm going to use this, and this angle would be 60 degrees, right? So I know this is then 60 degrees. So I'm going to use that. So we're going to do sine of 60 is equal to the opposite. So this is to the x. So sine of 60 equals x over the hypotenuse, which is 6 meters. Okay, so now I can solve that for x, and I get for x I get 5.19 meters. Okay, so the x component of this vector is 5.19 meters. Now, if you don't believe me that these would give the same angle, they will, or give the same magnitude using this angle of 60 to find x, or using this angle of 30 to find this x. Keep in mind that if we do this triangle, we are going to be using cosine of 30, which is going to be the same as the sine of 60. So they both will give us 5.19. So then we use cosine of 60 equals y divided by 6 meters. And for this, we get a y of 3 meters. Okay, so we see that for the red vector here, the components are a northward vector here of 3 meters. So I'm going to do vector 2 in my table, and it's got a north component of 3 meters. This is 5 meters. It's got 0, it's south because it's not in the south direction. And then it's got a component that's in the east direction, 5.19 meters, and then 0 in the west. Okay, so let's actually, can we make this a little better? 5, whoop. And then 0. Okay, so then vector 3 is going to be our blue vector. So let's go over here and work on that. Blue vector in. So now we're going to draw the components, and again, I could draw the x component here and then the y component down, or I could draw the y component down and the x component here. Just in terms of clarity, I'm going to draw these two. Could also do this. Keep in mind, for any vector, when you're resolving it into components, you can do either. So let's do, yes, we'll do this in that color, so teal. So there's the y component, and then we'll do the x component here like this. So there's the x, then we know this interior angle must be 50 degrees. So then we've got the sine of 50 degrees is equal to x over, now this angle, this magnitude of this vector is 7 meters. So sine of 50 equals x over 7. And that, if we solve that for x, that gives us an x value. Our x value is 5.36. And then, of course, we do cosine of 50 equals y over 7 meters. Okay, and then that gives us a y value of 4.49 meters. So we can put these in our table, and we see this. Now, the y component is in the south direction. So for vector 3, we're going to have 4.49 meters in the south. And then the x vector is in the eastward direction. So we're going to have 5.36 in the east. And then these become 0. So then, now once we've added all our vectors up, once we've done that, what we can do now is total the vectors, the components that we've made. We can total them up at the bottom and figure out what would the remaining two vectors look like to find the result. And so we do that, and we see that the net result is 3 meters south, and then 4.49 meters, 3 meters north and 4.49 meters south. And then in the east direction, if we add this whole column up, we have 0 in the west, so we can put a 0 there. That's easy. And then this column would become 15.55. So we do that now. The north and the south vectors, they're going to add up to make a combined vector. And I'm going to draw the combined vectors over here. They're going to make a combined vector south of 1.19 meters, right? Because a 3 meter north and a 4.49 meter south vector would subtract from each other, and what you'd be left with is 1.49, not 1.19, this should be 4, 1.49 meters south. The east vector is the only vector in the east-west direction, so then we'd have an eastward vector. Oh, let's do that blue. So we'd have an eastward vector of 15.55 meters. So then our resultant would just be from the tip of this vector to the, or from the tail of that vector to the tip of this vector. So this is what we'd be finding. Now, I know it doesn't look exactly the same as it does up here, but that's because this 7 meter vector is not to scale. It really should be longer than the 5 meter vector. So in real life, it should have ended maybe down here, which then would have given our resultant kind of this direction here that we're seeing, right? Okay, so that's why I like doing it with math, because it doesn't have to be drawn to scale. So now all we have to do is the Pythagorean theorem to find both the magnitude of this and the angle. Let's find this angle here. Okay, so I'll do the Pythagorean theorem. I get a magnitude of 15.62 meters, and then let's do the inverse tangent to get the angle. The inverse tangent, I get an angle of 84.5. So again, looking at this angle, that's going to be 84.5 degrees, and we're going to call this direction east of south, right? So this is east of south. Of course, it would be easier here if I draw on this triangle. This angle would be 5.5 degrees. That might be an easier angle, and that's 5.5 degrees south of east. but we could use either one as we saw in the last video. So our final answer, 15.62 meters, 84.5 degrees east of south would be our resultant vector. Hope you had fun, and look for more practice problems on iTunes U, and make sure that you get good at this. It'll make the rest of your year that much better and easier.